All right, energy in chemical reactions. We have talked about this a little bit before, but we're going to delve more in depth. And we're on page 100 if you missed that. So there are two main types of energy. Those two types of energy are kinetic energy and potential energy. Who knows what kinetic energy is? You do not have to tell me. I just want to know if you think you know what it is. I got 1, 2, 3 people, 4, 5, 6, 7, 8, 9. Okay, the rest of you don't know what kinetic energy is? Okay, so we're going to learn kinetic energy is the energy of motion. Okay, so kinetic energy is the energy of motion. How many of you know what potential energy is? Okay, I got most of you again. If you don't know what potential energy is energy that is stored. So kinetic is motion, potential is stored, and the abbreviation for kinetic energy is Ke. The abbreviation for potential energy is Pe. The law of conservation of energy is very much like the law of conservation of matter in that it says energy cannot be created nor destroyed. It can only be transformed from one type of energy to another. And if the two main types of energy are kinetic and potential, then the total amount of energy is the kinetic plus the potential. Because we cannot create nor destroy energy, total energy will always remain the same, but we can either gain kinetic energy and lose potential or gain potential and lose kinetic. Okay, one of them can go up and the other can go down. Energy is measured in either joules or kilojoules. Kinetic energy in terms of chemistry, in terms of particles, kinetic energy, we are looking at three types of molecular motion. There is vibrational motion, which looks like one of these three things. There's bending. You guys are going to do this with me. You're going to show me bending. Oh, that was terrible. Okay, you need to give yourself enough space to do this. In the middle is a carbon. On each side is an oxygen. Show me. Carbon, oxygen. Molecular bending. Okay, that's molecular bending. All right. We also have symmetric stretching. Show me stretching. Okay, so this is stretching. So these are both types of vibrations. Vibration, vibration. And then we also have asymmetric stretching. Show me asymmetric stretching. Okay, so we have vibration, vibration, and vibration. Those are all three types of vibrational kinetic energy. There are two types of rotational. So if you have a molecule that is linear, okay, you can have that molecule spin like this. Yes? Now, I can't do the next one because it would involve me flipping my feet over my head and doing like a handless back front flip. Okay? And I cannot do that. I could never do that, even when I was a young child and had energy and things like that. Can't do it. But you can imagine if we had a pen like this, you have one rotation like this, and then you have the other rotation like this. Yes? Okay. Translation. There's one type of translation, and that's just you move from one place to another place. Yes? And so you can get molecules doing all of these things. They can be vibrating and rotating and translating. Yes? And all of those things represent kinetic energy. The more a molecule does any of these motions, the more kinetic energy it has. The faster a molecule moves in any of these ways, the more kinetic energy it has. Okay? So there are some molecules that are not able to vibrate in the same way just because of their structure. And so they would have less kinetic energy, but you could give them more kinetic energy by heating them up, and then they would move faster. Okay. Temperature. This is a word that you need to know the definition of. Because if you tell me temperature is how hot it is, you will get a 0. It's not how hot it is. It is a measure of the average kinetic energy. So temperature is a measure of the average kinetic energy. That's why thermometers work the way they do. If we imagine that we have a thermometer, okay, and it's got mercury in it, Hg, okay, that's a terrible thermometer, but that's okay. And you've got all the little Hg atoms in here, yes? And let's say we're at 0 degrees right now, and so they're not moving very fast. When they start moving faster, they also start to take up more space, yes? Because they're just moving more, and it's like they need more room to kind of move around in. And so as they move faster, the volume of the mercury increases, and the mercury will end up at a higher place on the thermometer. So that's how a thermometer works. Okay, it's just the volume expansion of the liquid due to the particles moving faster. So you don't need to know anything about that. You just need to know that if you have more kinetic energy, you have a higher temperature. So if you have faster molecules, that's more kinetic energy, that's a higher temperature. If you have slower molecules, that's less kinetic energy, that is a lower temperature. So that's the takeaway from that. In chemistry, potential energy is energy that is stored in atoms and the bonds between the atoms. And it can be released or formed by various chemical reactions. Chemicals with a high potential energy, do you guys remember high potential energy things are unstable, right? This is at a high gravitational potential and it's unstable. It would rather go to a more stable position where it has a lower potential energy. So low potential energy is more stable. High potential energy, less stable. So the energy transformations that we are concerned with in chemistry is if we take kinetic energy and we transform it into potential energy. And if that's the case, what is happening to our kinetic energy? Is our kinetic energy going up or down if it's being transformed into potential energy? It's going down, and the potential energy is going up because we're taking some of the kinetic energy away and turning it into potential energy. So if kinetic energy is going down, the molecules are going to move slower. That means the temperature is going to decrease. However, because the potential energy also went up as the kinetic energy went down, the total amount of energy will stay the same. If potential energy is transformed into kinetic energy, that means we're losing some potential energy and we are gaining some kinetic energy. if our kinetic energy is increasing, the molecules are going to move faster. Therefore, the temperature is going to increase, and the total amount of energy still stays the same. So let's look at this in the context of a chemical reaction. Say you have some reactants that have 2 kilojoules of potential energy. Okay, so we got our reactants here, and they have 2 kilojoules of potential energy. And we have some products that have 12 kilojoules of potential energy. Our products, the potential energy is 12 kilojoules. Because energy is conserved, that means the total energy before the reaction must equal the total energy after the reaction. So this 10 kilojoules here, why is it not getting any bigger? There we go. This 10 kilojoules here is kinetic energy. So our 2 plus 10, that's 12 kilojoules in total energy. And over here we have 12 kilojoules in total energy. Is this reaction absorbing heat or releasing heat? Now, heat is really a measure, there are better definitions. Heat is really energy moving from one place to another, but I'm gonna say that heat is like the kinetic energy, okay? Is this reaction absorbing heat or is it releasing heat? And remember, heat is like the kinetic energy. And here is the kinetic energy. So is it absorbing heat or is it releasing heat? Are the 10 kilojoules going in to the reaction or are they coming out of the reaction? They're going in. Okay, so when we say absorbing means going into the reaction. And if we say releasing, that means going out of the reaction. So if we look at that and we say, it's on the reactant side, therefore it is going in to the reaction. Okay, so it's going into the reaction, so it is absorbing heat. And this is going to require a little thinking about. Is our temperature getting higher or lower as the reaction proceeds? Why higher?
So it's kind of like defined by the reactions that kinetic energy increase
Okay, so here's all our energy. In the reactant side, we have potential energy, 2 kilojoules, and we have 10 kilojoules of kinetic energy. In our products, we have 12 kilojoules of potential energy. Have we gained kinetic energy or lost kinetic energy? We lost kinetic energy. There were 10 kilojoules of kinetic energy at the beginning, right? In the beginning, we had 10 kilojoules of kinetic energy. Do we have any kinetic energy in the products? No. What happened to that 10 kilojoules of potential energy? Did it disappear? Remember, energy cannot be created, it cannot be destroyed. Yes? It got transformed into kinetic energy. So that 10 kilojoules is now part of our potential energy, right? So 10 of these kilojoules in here are now those 10 kilojoules from before. Okay? And still have our original 2 kilojoules in potential. That didn't go away. It just stayed there. So if our kinetic energy is decreasing, is the temperature going up or is the temperature going down? Down. All right? And so we are absorbing heat and the temperature is going down. So I want you to just think about that for a little while, because most of the time people hear, I'm absorbing heat, I must be getting hotter, my temperature must be going up. But we are absorbing heat, then transforming it into potential energy. Yeah? So anytime you hear absorbing heat, you need to add on, we're absorbing heat and we're transforming it into potential energy. Otherwise, it makes it sound like it's going to get hotter. So here's our example. You can just see it's a little bit expanded here. The total energy before, 12 kilojoules, is equal to the total energy after. If we were to do this on a graph, this is what we call a potential energy diagram. And on the x-axis, we have the direction of the reaction. So all that means is we have the reactants at the start and the products at the end. Okay, so we have reactants here at the start, and then we have the reaction taking place, and then we have the products at the end. So the reaction is progressing as you go from left to right. You have reactants, you have reaction, then you have products. That's our x-axis. The y-axis is the potential energy. And so, if we were to graph this, our reactants had 2 kilojoules of potential energy. So our reactants are at the 2 kilojoule mark here. Our products are at the 12 kilojoule mark. 12 kilojoules. Okay? So our potential energy has increased by 10 kilojoules. Is that straightforward enough? Yeah? Okay, cool. You're going to be responsible for being able to draw these graphs, all right, and interpret these graphs. So maybe I give you the graph and I say, what is the potential energy of the reactants? But I haven't labeled it reactants. I say, what is the potential energy of the products? But I haven't labeled it products. Okay, now what the heck is this wibbly wobbly arrow? That is showing that during the reaction, kinetic energy is going into the chemicals. Kinetic energy is being absorbed. During the reaction. And transformed into potential energy. Now, when you draw these diagrams, you are not going to have to draw that squiggly line, okay? So the squiggly line is not required. I'm just putting it there so you can see, why did the graph go up? Where did that extra energy come from? That extra energy came from kinetic energy being absorbed, okay? So kinetic energy was absorbed, it was transformed into potential energy, and therefore kinetic energy decreases, therefore the temperature will decrease. This is what we call an endothermic reaction. How many people have heard of an endothermic reaction before? Okay, if you have, that's great. If not, this is new vocab for you. Endothermic reaction kinetic energy has entered the system and has been transformed into potential energy. Another way of saying that is endothermic. Why am I writing a space in between? Endo, enter, thermic, heat. And remember, heat, even though that's not really what it is, heat is like the kinetic energy. Okay, your physics teacher can take that up with you. They'll be like, heat is not kinetic energy. Heat is just the movement. It's the movement of, never mind. Heat is too complicated to explain, and I've never really loved it. So, yeah. Talk to your physics teacher about it. Okay, now we have a new reaction. Let's say you have some reactants, and these reactants have 9 kilojoules of potential energy. You have some products, and they have 1 kilojoule of potential energy. That is a difference of how many kilojoules? Super difficult, 9 minus 1 is 8. So that's a difference of 8 kilojoules. We started with 9 kilojoules of potential energy, and we finished with our products having only 1 kilojoule of potential energy. And remember, that energy cannot have been destroyed, so it needs to go somewhere. Where is it going? It has been released into the environment. Okay, it's coming out of that reaction, and if you happen to be so lucky as to be nearby, it will feel nice and warm. Yes? So this heat, this kinetic energy, which we can also call for now the heat, has been released to the environment. So now all the particles are moving faster. And if the particles are moving faster, what happens to the temperature? Okay, what is temperature? It's a measure of what? The average kinetic energy. And remember, the higher the kinetic energy, the faster the molecules. Okay? And all of a sudden, we have more kinetic energy than we did before. How much kinetic energy did we have on our reactant side? How much kinetic energy on the reactants? Is there anything that says Ke in that yellow highlighted reactants? No, we had no kinetic energy. And then over in our products, we have 8 kilojoules of kinetic energy. So we went from no kinetic energy to more kinetic energy, and therefore we have higher kinetic energy, faster molecules, and therefore the temperature will go up or down. So imagine this reaction has released energy, and maybe it's in, this container here, and I hold on to it, and the reaction's taking place in this container, and the heat is exiting and is coming out into the surroundings. What's happening to the molecules in my hands? They're being bashed by these molecules that are now moving faster. If they're being bashed by faster molecules, what's going to happen to the molecules in my hand? They're also going to move faster, right? It's like if you throw, I don't know, if you throw a ball, like if you've got a pool ball and you hit a pool ball, and it's moving fast, whatever ball it hits is also going to move fast. If you have a pool ball and it hits another ball and it's moving slow, the other one is also going to be moving more slowly. So these molecules in the reaction are moving faster, and they cause a chain. It's like a domino effect. That energy gets transferred all the way into my hand. And if the molecules in my hand are moving faster, does that feel hotter or colder? That feels hotter. Okay? So if we have higher kinetic energy, the temperature will increase. Okay? High kinetic energy, high temperature. Low kinetic energy, low temperature. I can never tell with you guys whether you get it or not. I can tell from some of you, but the rest of you, I have no idea. I have no idea if I should be repeating myself more, if I should be expressing it a different way, or if I should just move on. And you're like, oh my God, you've said it 7 times. Like, where are we at? Are we at a thumbs up? Are we at a thumbs down? Or are we at a thumbs in the middle? Okay, I got some thumbs up. I got some thumbs in the middle. Okay. So we're mostly kind of getting there. I didn't see anyone with a thumb all the way down. So we're just going to go on to some more examples, and let me know if by the time we get to the end of that, it's not making sense, okay? So here's our reactants. We have 9 kilojoules of potential energy. Our products have 1 kilojoule of potential energy. And we also have our 8 kilojoules of kinetic energy. But you'll notice on both sides, 1 plus 8 gives us 9 kilojoules, which is equal to 9 kilojoules. So the total energy is 9 kilojoules. The total energy is 9 kilojoules. Graphically, what does this look like? What goes on the, but just before we look at the graph, what goes on the x-axis? You guys aren't paying close enough attention. If you're paying close enough attention, you should be able to tell me what goes on the x-axis. Direction of reaction. Now, there are other things this can be called. This can be called the progress of the reaction. Okay, so those are a couple of ways you might see it. What goes on the y-axis in a potential energy diagram? Potential energy, shocking. And what is the unit of potential energy? Kilojoules. I'm going to make a little change. I'm going to make it kilojoules per mole. Okay? No big deal. It's just that I found that last semester, people were getting really wound up. When is it kilojoules and when is it kilojoules per mole? Just always make it kilojoules per mole and then we'll be happy. Okay? Always kilojoules per mole. So if I write kilojoules, I really mean kilojoules per mole. All right? I need to update my booklet so it reflects that. But sometimes it's just easier to write kilojoules because it doesn't get as mucky. Like it's easier to see. So here we have our reactants at 9 kilojoules. We have our products at 1 kilojoule. And here is where the reaction takes place. And what is happening during the reaction? During the reaction, kinetic energy is off you go. It is released. Okay, kinetic energy is released during the reaction. Some of this potential energy is converted into the kinetic energy, which is then released. So do we have more kinetic energy than before or less kinetic energy than before? We have more kinetic energy than before. Is our temperature going up or is our temperature going down? Remember, what is temperature a measure of? I'm going to write this down until you guys can tell me because this is an important thing. Temperature is a measure of average kinetic energy. If we have more kinetic energy, is that a higher temperature or a lower temperature? That's a higher temperature, so the temperature is going up. So during this type of a reaction, temperature, come on, temperature increases. Okay. All righty. So, yeah, that's it, I think. Yeah, that's it for that. All right, now this kind of reaction where we have released energy, energy has exited the system, this is called an exothermic reaction because kinetic energy has exited the system. Potential energy has been transformed into kinetic energy, and that kinetic energy has then exited the system. So exit heat. Exothermic, exit heat. Reading check number 1, complete on your own sheet of paper. I'm going to have you do that for homework. Oh, yeah. Okay. 6.4b. No. Actually, what I'm going to have you do is, because I also want you today, this is your introduction to this. So pages 103 and 104. You are going to do those. But what did we finish yesterday? We finished predicting the products for all the types of reactions. Yes? So at this point, you are able to predict products and balance all the types. So on pages 94, 95, 96, and 97, there are a whole ton of reactions. And they're all mixed together randomly. So there are some synthesis, there are some decomposition, there is some single replacement, there is some double replacement, there's some neutralization, there is some combustion, okay? There is a reminder up here, how do you recognize them? If you have synthesis, you have an element plus an element. If it's decomposition, you have a compound. Single replacement, you have an element and a compound. Double replacement is a compound and a compound. Neutralization, you have to have an acid and a base. And hydrocarbon combustion, you need to have a hydrocarbon, and your second reactant will be oxygen. For single replacement, you should be using the activity series. This is on page 94. Double replacement, you should be using solubility chart. And you do not, if you're interested in doing the enriched, you're going to predict the states for everything. There's some tips there for it. If you want to do enriched, you can write the formula for organic compounds. For double replacement, you need to write the states, okay? Everyone write the states for double replacement. How many people do I have today? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay. First 5 people who are done get 5 out of 5. Second 5 people done get a 4 out of 5. The third 5 people done get a 3 out of 5. The fourth 5 people done get a 2 out of 5. Do you know why I have to do this? Do you have any idea why I have to do this? So people don't sit around with their finger in their ear right? Everybody work. And if everybody's working, I may take it back. Okay? So work hard, work fast. Mostly work hard. I don't need you to be super fast, I need you to be working hard. So, Chem 11, we have pages. 94 and 95. And the other one was 103 to 104. I don't know what anybody wound up about. You guys worked really well last day. Just keep working really well. I'm projecting my green lines onto you. I don't know. I apologize. Yeah, no problem. Does anyone have a blue sheet? Yes. Yeah, I'll grab one. Reaction. So you're gonna write reaction. Yes. Yeah, but you can do that word. I'll grab you. Yes. Oh, you don't need one. Not really, no. Unless you can't multiply 2 and 3, in which case that would be problematic, but. Anyone else need a blue sheet? Three times 2 plus 2, I don't know. Yeah, and it'll be slightly different than that, it'll have the same number of hydrogens in it. Yes, yes. So folks, when you see the little diamond, you can look, if you don't want to do the enriched part, you can look at the bottom of the page. I think I'm missing butane. Missing butane? I think I'm missing butane. Butane. Folks, sometimes in combustion, if you're doing the states, you'll see H2O given as a gas because it is burning, so it's at a high temperature. So water is gaseous, but if you put it as liquid, that's fine. Okay? So if you're, and that's only if you're doing the enriched stuff, in combustion, water can be a gas, but if you put it as liquid, that's fine. Doing this one even doing shells. We've done also on solid. Thank you very much. How do you do this? Okay, so the trick with these ones is that that's your positive ion and that is your negative ion. Okay, so rather than combine your outside ions and your inside ions, you have to put a little more on polar, you know, say, find a positive ion, my negative, positive sign. But if you always remember that that's your H, then go to OH, then you can figure out whatever's left over. That's what's good. So, yes, and that's just because it is so small. I need something to write with. So for that one, it's pick up that H there rather than the full, right? So instead of that, which is why it's not instead of, yeah. I'll do it again. Yes. Yes. That's liquid. Yeah. Because it's a largest molecule of hydrogen bonds. Okay. Yeah. Okay, so carbon and hydrogen then oxygen. And to do like doubling the times halves of the current. So you're right, that would be a 3. Yeah. And then the 7 hydrogens. But that's not more, but you have an odd number of numbers, right? Odd number. Oh, hang on, no, you don't, you have 8 hydrogens. 8 hydrogens. Not in combustion, never OH combustion. Okay? So we have 8 hydrogens, you have 8. Now that's oxygen. It's 8, so that has to be 8. And then over here we have 3 times 2 is 6 plus 4. Yeah. And then over on this side, we have 10 minus 1, because we've already taken care of. So we need 9. All right. Yeah. That I forgot. Yes. 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 And if you don't like doing the halves, you can always double it. Molar. What that means is if it says molar, it's aqueous. No, it's just there to let you know that if you're
big states, it's easy. Yeah. And your question. You don't need to do anything. The only reason this is here is to let you know if you're aware of the substances they use. So if you are to these states, that will let you know that anyways, but you don't need to do anything. Yeah. Yeah, so the opposite, yeah. So we have 3 times 2, 6, plus 4. Only, so that's 10. The only here we have 5 times 3 is 10, plus 1 is 11. So we don't actually want 5. We want 9 oxygen. To do that, we use 9. Then what we will do is we multiply the products. If the half makes you uncommon, not like that, start by reducing here and balance the rest.
So it's looking at it, it's not a full. Like,
You can do a half. Halves. Okay, but when you finish up, you should make them whole numbers. Okay, you can just have to be balanced, but that will let you to make. Good? Okay. Sorry. Yes. Yeah. Okay. Anytime you have a hydrocarbon and oxygen, hydrocarbons have carbon and hydrogen. Hydrocarbon, we might also have. Don't switch anything. It's always get the same product. CO2 and H2O. Plus H2O. How did it do that? Okay, what I want you to imagine is that this molecule explodes and all the atoms are separate. Okay, this atom explodes and all the atoms are separate. Just like that video we watched. Remember that one? Okay. That's what's happening here. All the atoms are split apart and then they go. And then one carbon says, I'll take 2 of those oxygens from another carbon says, I'll take 2 of those oxygens. So all the other carbons have 2 oxygens. Hydrogen say, 2 of us will have an oxygen. So basically you're just smashing them into smithereens and then putting them back together. How do you know there's an H2O? Because you're right, it's the same every time. You know, there's nothing exciting to predict. There is always true. Yeah, always, 100%. Unless you got something else exciting in here, like a vector and nitrogen, there would be something else. How are we doing? Anybody got a question? Yes. By the way, I'm not doing that time thing. That was ridiculous. So. Yes. Sorry, my oxygen now. If you're given a decomposition, then it is going to be. Oh, okay. I will say if I want it to be anything like I will say this, or I will say this molar, whatever. So you can see here, if I see the acid, you can assume the acids are this, and then we say sodium hydroxide solution, so that's the solution. Yeah.
So there's one,
That's all I'm gonna do, so that's what he says. It's a molar, it's a solution, and it's.
yeah,
Yeah.
but then synthesis.
Synthesis is gonna be solid, yeah. See that proper. Chloride, so what does that do? That tells me that copper is plus. Think that too, tell you that. Chloride. Table. It's fine. Yeah. So what's the form? Plus and still nice. You mean the positives and negatives.
So.
That excludes the two atoms. Yes. Yes. Basically, still too. That's also nice and fun something. First of all, that's an option. This is opposition. Not separate. There's no fluctuation between them. All the pluses are all of these have two races. So, no, but just one, nothing else here, right? Plus side, yeah. I have two comments. Anyway, some of them are being heated, some of them are being, together. Obviously, this will not next year. Okay, but, yeah, either you're heating it or you're applying electricity to it, that's also a possibility. So it's like, split the two elements up. CL. Check this in, right? Diet comments. Yeah. Okay. Sorry. Okay. Oh, and folks, on page 95, I forgot to put butane on there. So if you don't know butane, if you haven't learned how to do those, butane is on the board on page 95. Okay. No, that's just for, double replacement, because, water. And that is our main substance. So if you have water before. If it's double replacement of both aqueous, then both products are aqueous, then there's no reaction. it has to be a product. It's just your thing. Yeah. That is. Or like, I'm just a little smoker. Good. Next unit is psychology and solutions. It's a lot like this. So basically what we're doing is reactions and we're putting it together with moles. So it's like if it takes two hydrogens to react with one oxygen, then if I have 8 moles of hydrogen, how much oxygen do you need?
I was thinking about.
Yeah. So those coefficients, they're just smaller conversion factors that are like a 2-to-1 ratio.
What is that?
right?
Yeah. Yeah, what is that?
How's it going, Alex? Good?
How are you doing, Ayush?
You're good? Okay, excellent. How's it going, Alex? Good? Okay, so let's do that. And here's my module, what are your development fail? Chlorine. Diet pumps. Yeah, okay, so chlorine. This. So that's. Yeah. So you're going to take over reactants. Yes, this one, this is correct, this one should be the type of reaction. Single replacement. Two things, okay? And, here you just have one. Okay? Yes. For double replacement, only for double replacement. Yeah. Folks, you only need to write states for double replacement unless you're wanting to do enriched stuff, okay? Yes.
I don't need.
Yeah. Yeah.
Would you write it as before each?
You have a choice, you can write it as, no, it would be C4H10O. Yeah, because what happens is that the H still stays, it moves, but you still have the same number. So you can write it as butanol, could be. Can be C4H9OH, or you can write it as C4H10O. And for the purposes of this, that's fine. If we're doing more organic chemistry, you want it written like that to make it obvious that this is alcohol. Alcohols always have that OH grouping, right? So, yeah, but this is perfectly good. I'm sorry, I'm doing it.
So sorry.
Oh, so if you had after tabs, so if you didn't after tabs, like doubles, maybe the other way. So you shouldn't have 1,000 in final. In final. But you don't have to show the work, you can just be like, if you have this, you can just. Yeah. Right? That's just like that. No. Right. Do you have questions? Yes, sorry. I was like, did I hear something? Okay, so here's the other. When someone is in this, I would do something like say, what? Or I'm gonna say, switch. Okay. Otherwise it's solid, because the thing is that there's just no water here. Right? Like, some reactions have to take place. The whole replacement doesn't work. It's at least one of the reactions. No, actually, both reactions. Should be solid. So if it's solution, it's going to say either or zero, or if there's gas. Oh, this is no bad, but yes. Here, do I want to go over? Not sure about that. Okay. So let's try some data on that then. Okay, so let's try to get this up. So we're going to call it clear. Okay, so that's when you want to do that. Actually, this one. Always CO2 plus CO2. Yeah. So anytime always CO2.
I mean, it sounds.
There's no one.
And then wow. Okay.
I just thought you nobody did this. I will be just getting I will tell you. I'm gonna tell you because I'm here.
I didn't even know you took out.
So in town, there's a solid.
That should be like,
So this is a solid.
You know, I don't think the father really
Because there's no. Always get water, so it doesn't matter the chemistry on the solid or.
This is not bio.
It's already happened. Neutralization. Okay, not for combustion, okay, not here, don't go there. For neutralization. Okay, okay. Yeah. Okay.
Sorry.